Hi everyone, thank you for attending this webinar. Today we'll talk about functional safety non-volatile memory IP solution for Autotronics. My name is Parker and I'm a neophyte IP designer from eMemory Technology in Zhubei, Taiwan. Before we start, I'll briefly describe why this topic is arising more and more in this industry. First, I'll talk about autotronic demands, followed by the importance of functional safety. To conclude, I will highlight the key features of eMemory solution. To satisfy a variety of applications, I'll also disclose the structure for ASIL-B and ASIL-D. Imagine this situation. I'm driving my car on the highway, and I turn the adaptive cruise control on. The vehicle will control steering, acceleration, and braking automatically, so I could relax while I drive. But suddenly the radar controller IC has malfunctioned. How should a vehicle react? How does a malfunctioned IC react? The reaction of the IC in automotive applications is not the same as consumer IC. For most consumer IC like cell phones, we just need to restart our device while it gets stuck. The functionality of the automotive IC is not as simple because it affects the human lives directly. That's why the automotive IC with function safety needs to consider. As vehicles become smarter and smarter, the automotive IC play a key role and assumes high responsibility for both vehicles and human safety. As cars become smarter, the electronic system costs also increase. In the 1950s, the cost of electronic system was less than 1%. In the 1980s, high-performance and high-efficiency engines were developed. Engines with electronic fuel injections become the standard for premium cars. It raised the electronic cost to 10% of the total car cost. Because of this, the car manufacturers and consumers not only focus on the car performance but also car handling and driving safety. In 2000, the airbag system and the braking system and electronic stability program were introduced and has since matured, raising the electronic system cost to 22%. For 2010, 2%. Advanced driving assistance systems, such as the active brake system, active cruise control, auto parking system, and comprehensive infotainment system were introduced, and raising the electronic system cost raises to above 35% of the total car cost. Okay, the automotive industry comprises a wide range of the companies and organizations involved in design, development, manufacturing, marketing, and selling. This, of course, also includes the semiconductor industry. The chip shortage during the COVID-19 pandemic demonstrate how important the semiconductor industry is to the automotive industry. The major driving force of automotive chip growth is a driving assistant, also known as the autonomous driving. We could roughly separate the car development history into three stages. The previous generation, no automation at all. The present generation, partial and conditional automation. And the next generation is full automation. The difference is the driving responsibility of the drivers or the car. The steering wheel, brake, and throttle are full controlled by driver or by the vehicle. Here we talk about functional safety. As the vehicle becomes smarter, drivers rely heavier on the ADAS, advanced driving assistant, and drivers get more comfortable when driving with the partial or conditional driving assistant. For the car, it's a huge responsibility to ensure every system is normal at each moment. The car designer needs to consider how the car reacts if the system is more functioning. That's what we refer to as functional safety. Functional safety is like a safety guard that protects the driver, passengers, and pedestrians if the system fails. Automotive safety integrity level could be determined by this flow. For example, which function failed on the airbag system, what hazard could happen, the airbag could explode inadvertently, how likely harmful controllable is the hazard, how likely is the hazard. It depends on the failure rate of the electronic system. How harmful is the hazard? The exploding airbag will cause the driver to lose control of the car. Based on this analysis, the ASIL level could be determined. The lowest requirement is the ASIL-A and the highest is the ASIL-D. This page shows the typical automotive classification. We can see that most of ADAS require ASIL-D. That means the electronic component in the system needs to satisfy the ASIL-D requirements. What's eMemory solution? eMemory is dedicated to provide reliable non-volatile memories. We provide 4 categories for different customer applications. Let's focus on IP categories: high temperature, zero failure AEC-Q 100 grade 0, functional safety ISO 262, ASIL-B, and functional safety ISO 262, ASIL-D. The major difference is the method of failure reduction and safety measures. For the consumer grade, we use quality management for the failure reduction. For the automotive grade without functional safety, we use the comprehensive test modes and error correction code (ECC). For the functional safety ASIL-B category, the comprehensive test modes, power monitor, power on-read non-pattern, error correction code ECC scan by software pattern check, and address fault detection are involved. For the functional safety ASIL-D category, the comprehensive test modes, dual-core Lockstep architecture, error correction code, and ECC scan by software pattern check are involved. Each category has related analysis method to ensure the quality meets the requirements. For consumer grade, the IP design will follow eMemory's best-known method to prevent design failure. For AEC-Q 100 automotive grade, the IP design will follow FMEA analysis result to minimize the risk of failure. For automotive with the ASIL requirements, the IP design will follow FMEDA and safety manual. FMEDA is for failure rate quantization. By involving the failure rate of each subsystem and diagnostic coverage of the safety measures, the residual failure rate could be assessed. In the next few pages, I'll introduce some safety measures. The first is the comprehensive test modes. It's an analog signal monitor mode. The customer could monitor a critical signal in the chip's probe stage or field site. eMemory IP, and the reference current is the most critical signal. It's a benchmark to identify erase state or program state cell. The safety measure is called power on read known patterns. We have designed predetermined patterns in the cell array. The predetermined ROM data will be checked during the power on sequence, except for the main array. Other blocks would be checked by this power on read known pattern mode safety measure. This safety measure could ensure the brief function of the whole system. As we introduced previously, the reference current is a benchmark for identifying the memory state. For stricter criteria, The benchmark not only identifies the memory state as program or erase state, but also identifies how much margin for failure. When the reference current is adjusted, the margin of memory could be determined. This safety measure, known as the external reference current read mode, could ensure the health of the memory. The address fault detection is so important that even error correction code design was adopted in this system. For a traditional error correction code design, the safety measure won't cause alarm if the address decoder accessed a wrong address. This failure can be alerted by the error correction code. Here we introduce the address fault detection to detect any malfunction of the address decoder. The concept is to encode the word line and bit line signal back to the address. By comparing the encoded address with the input address, we can measure the correctness of the address decoder. This safety measure is called dual-core lockstep architecture. The dual-core lockstep architecture includes two identical non-volatile memories and two error correction codes. The storage data is complementary to each other. The read operation of these two memories is non-synchronized. This architecture could enhance the diagnostic coverage rate for common cause failure. By comparing the readout data between two memories, we can ensure the correctness of data stored in a non-volatile memory. To summarize the eMemory Automotive IP solution, three categories were introduced: zero failure ASIC 100, ISO 26262 ASIL-B, and ISO 26262 ASIL-D solutions. For the zero failure ASIC 100 standard IP, that's an error competitive solution when customers handle the functional safety of storing data on their side. For storing data with functional safety, eMemory provides ASIL-B and ASIL-D solution for a Neobit product line. That concludes our discussion of non-volatile memory IP solution for Autotronics. Thank you everybody for joining us.